Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. I have a video for you here just to demonstrate basics of light. So let's go ahead and play that. Pretty cool, huh? Yeah, let me go ahead and get right over to here. There we go. So the whole idea here, just in the video, is that you have different types of light which an object will look differently under. I mean, kind of state the obvious there. And the Crab Nebula, I just thought was a good example of this. You notice that in something like visible light, for example, this bottom corner, you see a whole lot of dust, but you don't see an actual star there. That's because you're looking in the wrong type of light. The star in the center of this cloud is so hot, and which we'll get to later, is so hot that it does not emit much visible light. And in fact, you really can't see that star until you get all the way up into X-rays, right? Right there, boom. Right there in the center. That is a wicked, wicked hot star. Just like Tycho Brahe, who had noticed a supernova in Cassiopeia b, this is another supernova remnant. A star previously exploded, and the cloud surrounding that star is actually the remnants of that explosion moving outwards. Now, this is one of the earliest historical supernovas ever recorded, and it's accredited to Chinese astronomers in the year 1054 CE. So what we're going to talk about today are the basics of light. And the first thing that the video highlights for you is that there are different types of light. Sometimes you'll see the term electromagnetic spectrum. Okay? That's a fancy way of saying it. I'll just use the word light, and I'll try to be more specific when I'm talking about visible light, i.e. the light that our eyes receive, that our brain can interpret, that allows us to see. Okay? That is actually a very, very narrow range of possible light that is out there. I've listed for you other forms or other types of light, namely radio, infrared. Of course, we have our visible. Then we have beyond visible, which would be the ultraviolet, moving on into X-rays and gamma rays. Okay? These would all, to an astronomer and a scientist, still be considered light. Okay? And the key is that when you look at an object for different types of light, okay, you get to see different things. Okay? The Crab Nebula showed that in visible light, you can't really see the central star. What you get to see is the cloud of gas and the fine features surrounding that star. If you want to look at the star itself, you better go to X-rays. Well, say, for example, you don't want to see the cloud, you don't want to see the really wicked hot star, you want to see stars behind the cloud. Well, in that case, infrared light is very helpful because infrared light can pass through dust very easily. The picture for you here on the right-hand side is the Orion Nebula, and it'll oscillate between visible light, and this is infrared right here. So it'll just flip back and forth to give you a comparison. So this is not only in, astronomy. Scientists use this all the time, medical field. How about art history? here is a painting of Raphael's Madonna. I believe it's unsigned. Okay? Excuse me, I have it right here, unsigned. And so if you go up and you step up and you see the picture in visible light, this is what you're going to see. But if we want to say, look at, for example, if the canvas has been previously used, or maybe we want to get an idea about if Raphael sketches out his paintings before he actually fills it in. Maybe, for example, canvas is very expensive. Maybe there was a former painting underneath that Raphael said, oh, I don't like that. Let me do this new artwork instead. Okay? Reusing and recycling. Okay? So visible light won't be able to give you that information. Visible light will reflect off of the top layer and not show you anything inside the painting, beneath the top layer. Well, let's go ahead and use a different type of light. Okay? So because of various things, this is again an infrared. And for this instant, infrared light is very easily absorbed by charcoal, carbon. Okay? In other words, stuff that you would tend to sketch with first, easily erased. Well, for example, perhaps we're interested in knowing if Raphael made any mistakes. So we have the pre-sketch, we have the final product, but maybe there were mistakes in the final product. It turns out that for the period, one of the ways that you cover up mistakes when you paint is you use whiteout, right? You make a mistake writing in pen, you say, oh, I don't like that, you white it out, and then you can write over it. Well, in the time, the white color of paint was made by incorporating lead. Lead is very good at absorbing X-rays. So we can look at the same picture and using X-rays, we can see where Raphael used some whiteout, right? These white splotches indicate areas where he made a mistake with his paint. He said, I don't like it, it doesn't look right, let me white it out and repaint over it. And yes, the other nice thing about this is that this is a non-damaging technique. Okay? You don't have to take apart the painting. You don't have to scrape off layers in order to see what's underneath. So not just astronomy. This is used all over the place for various ideas, medical, art history, etc., etc. Okay, so let me give you an idea. So we're moving into chapter 5, and we are going to be using light. And in particular, we are going to be using light to infer quantities about distant objects. If I think about light for a second, okay, what observables can you tell me about light? You got it? Yeah, good. Well, for example, one of the properties that you can tell me is what color it is. Okay? Right? You look at a light, is it a red light, green light, blue light, et cetera, et cetera. So one of the properties that we can assign to light is a color. Now, the issue here is that color tends to refer to just the visible spectrum. Color is the brain's interpretation of light collected by the eye and then, translated. So how do we, what kind of color do we give to an X-ray? Okay? Right? I mean, that it doesn't jive. Our brain can't interpret X-rays, so color is kind of a bad way of communicating it. So what we do instead is we use a term called wavelength. You can think of light as being a wave, and the wavelength is the distance between two adjacent peaks. You could also define it as two adjacent troughs, or even more generally, it is the distance required for the wave to repeat. So almost like the period, right? The time it takes for an object to repeat, this would be the distance required for an object to repeat. Okay? And we will tend to use that as defining the type of light that we're dealing with. So if you're talking visible light, the wavelength and color are synonymous. If you're going beyond the visible spectrum, usually you'll find people talking about wavelength. The other, hopefully one that you came up with, is the intensity, how bright light actually is, or how bright light appears to be. Okay? So the amount of light, we'll put it this way, intensity, the amount of light that's being received. Okay? We'll go a little further on that, but that is an observable. You can look out and say, wow, that light's bright. Wow, that one's not. Okay? Okay. The last one I'll give you, it's the speed of light. Okay? It turns out there's a third property about light that we can say. It's that the speed of light is constant. Okay? So the speed of light, here, let me display this for you. There you go. The speed of light is used c. Okay? C represents the speed of light. And we've actually already used this in our discussion about unit conversions and the light year. Okay? The speed of light, c, is equal to 3 times 10 to the 8th meters per second. If you want to translate it, that is 186,000 miles per second. Okay. Turns out that is another property of light. Okay. It is related to the wavelength, the distance required for something to repeat, and another term, the frequency. Okay. And I'll go ahead and we'll do a little bit of discussion about where that comes from or how to rationalize our way through it. Okay? Now, from those three characteristics, the wavelength of light, the intensity of light, and the speed of light, we are going to be able to infer about 5 different things. The first thing that we can infer is the energy of light. And this one is, I'll just give it to you. Notice the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. Okay. Other inferred quantities, and we'll go through and discuss each of these in turn in subsequent lectures. But the next one is from the wavelength, and I should be even more specific, if I take light and I look at the wavelength, I can infer the temperature of an object based on the light that's being emitted, okay? The color of light being emitted. Pretty cool. Well, how about this? Based on, again, the color of light being emitted, we can sometimes get an idea about the composition of an object. Now, it has to be a very special type of emitted light, but we can get the composition based on that. How about this? The intensity. I mentioned the intensity and I said, well, that's an observable. It turns out that the intensity of light can be used to determine how far away an object is. We'll have to put a couple of assumptions in via our model, but once we have those assumptions in there, we can start estimating the distance to other objects based on how bright those objects appear. This one's really cool too. You ready? Done. Okay. The last thing that we'll be able to do is, again, using the color of light to figure out how quickly an object is moving, to infer the speed of an object. And that one in particular is extremely fascinating to me. This last one will very much help us get a new conceptualization of our universe. Okay, you ready for this? Let's get an idea. So rewinding, I want to give you an idea about wavelength, just a conceptualization about wavelength, and then we'll go into frequency. So those two are tied together. I just want to give you a good heuristic argument for why that is. So let's consider this for a second. Imagine a train comprised of exactly the same boxcar. So I've got them 5 meters in length. Okay? And imagine you're standing by the side of the train track, and this train, infinitely long, is going by you. Okay? 20 meters per second. First question, what's the period of the boxcars? You got it? Yeah, good. Okay. So, and again, remind ourselves, period is how long does it take for an object to repeat? So if you're standing here, you ignore the rest of the train. You're standing here, you see the start of one boxcar. The question is, how long do you have to wait until you get to see the start of the next boxcar, right? The train shifts by exactly one boxcar, and so it repeats, right? From your perspective, it looks like the boxcars are just continually repeating. Well, how do you get that? Yeah, hopefully you see that the period is related to how long the boxcar is. You know that if the train travels 5 meters, then you'll get a repeat. So the alternative question is, how long does it take for the train to go 5 meters? Well, you've got this. No fancy equations required. You know that distance equals rate times time. Well, I'll go ahead and use distance equals rate times time, except I'm going to move rate to the other side of the equation. So the time, how long it takes for the train to travel the 5 meters, is given by how far and how fast. So we'll plug in our stuff. So I'll use P for period, and we know it has to travel 5 meters in order to repeat. It's traveling 20 meters per second. Oh, goody. Notice that there's a meter in the numerator. There's a meter in the denominator. Okay. So I basically have, I'll write this as a compound fraction. I have 1 over 4, 1 over seconds. Okay. And if I want to get those seconds into the numerator, you multiply both top and bottom by seconds. Okay. And I have in the denominator 1 over seconds times seconds, so that cancels out. And I have seconds in the numerator. Okay? So what do you get? You get a period of 1/4 of a second. If you wait exactly 1/4 of a second, the train repeats. So, okay, good. So we have an idea about how to relate the period, how often the object repeats, to the size of the object, right? We can say, how long does it take for the boxcar to repeat? We're using the size of the boxcar to figure that out. Okay. So, next question. For the same train, how many boxcars pass you in 1 second? Yeah, you got it? Yeah, good. Well, you know that if it takes 1/4 of a second for one boxcar, in other words, that's the period, then you know that, okay, well, you could say, well, 1 second divided by 1/4 of a second equals the number of boxcars over 1, right? It takes one boxcar in 1/4 of a second. So how many boxcars do I get in 1 second? And you see very quickly that you get 4, right? X is equal to 4 boxcars. Okay. Note what you have essentially done is you said, hey, the number of boxcars is 1 divided by the period. Right? That's essentially what we've done. I mean, you could set it up as a proportionality, but the result is the same. Right here, 1 second divided by the period gives you the number of boxcars. Okay? So I'll go ahead and do that. Boxcars is equal to 4. Okay, now I'm going to define a term. The frequency is defined as the number of events in a second. Okay. So for example, in the case of our boxcars, we would say the frequency of the boxcars is 4 boxcars per second. And the frequency is simply defined as 1 divided by the period. Okay, so now let's transition to light. Okay? Imagine, rather than boxcars, you have light with a wavelength of 3 meters. And the typical way of representing light, again, is this wave, this sinusoidal wave. Okay? So I'm saying that, hey, the wavelength, lambda, is equal to 3 meters. If you have this beam of light, and you look right here, you can walk 3 meters down the road and see the exact same kind of thing. Okay? The speed of light I've given to you, 3 times 10 to the 8th. That's known as the speed of light, c. Okay? Question, what's the frequency of this wave? Go ahead. Does your approach actually change? No, good. No, nothing changes. Your approach stays exactly the same. The only thing that I have changed are the numbers. So if you want the frequency, we could get the period, right? The period is 3, the distance, divided by the speed. Okay. Oh, goody, goody, it's nice. Well, first of all, the meters cancel. And you notice I've got a 3 in the denominator and a 3 in the numerator. So we could cancel those as well. I'll do those this way. And so you get that the period is 10 to the negative 8th seconds, and I'll put in parentheses, per wave. Okay? It'll take 100 millionth of a second for this wave to repeat. Well, what's the frequency? Okay? Well, you could say, well, the frequency is 1 over the period. And now I've got the period. I'm just going to plug that in right here. Okay. And oh yes, good reminder, scientific notation, if I have a negative power in the denominator, I can rewrite that as the same number with a positive power in the numerator. I change the sign and I change its location, right? Of course, if you want to see that, you could say, well, multiply both top and bottom by 10 to the 8th. The mathematician's fancy trick of multiplying by 1. Okay. And so what I get is that for this light, I will get 100 million boxcars passing me every second. If I stood here and just counted, I'd get 100 million of them. Okay, so that gives us the specific relationship between frequency and wavelength. And I'll highlight for you, the shorter the wavelength, as this is constant, this always is the same. So as the wavelength gets shorter, your frequency inherently has to go up. That should make some intuitive sense. If my train cars are shorter and the train travels at the same rate, then more train cars must pass me for a given amount of time. Okay. And as I've mentioned before, higher energy corresponds to shorter wavelength. Okay. Now, what do you have to have memorized? Please have the different types of light memorized and their relative order. You do not need to know the specific numbers. Oh, if the wavelength is 100 nanometers, then what type of light is that? Shoot, you don't need to know those. Okay? There are 2 numbers you definitely need to know. Okay? And I'll give them to you here. Please, please, you need to have memorized that red light, red visible light, corresponds to 700 nanometers, and purple visible light corresponds to 400. Right? I want you to have those 2 numbers memorized so that you know the range of wavelengths for visible light. Well, I think that will wrap up the basics of light. What we'll do for the next couple of lectures is we're going to go through and work out those inferences, temperature of an object. We're going to work on the composition, the speed of the object, and trying to figure out how far away objects are. So I hope you're ready for some adventure. This will be the jumping point. We'll use these ideas in order to start studying stars and finding our way further and further into the universe. I hope you're ready for it. Thank you for your attention. Keep up the good work. I'll see you next time.